Okay, so I would like to start by finishing why we get the fast expanded decomposition. Like, although we have really finished all the technical thing in lecture already, but I didn't really finish it properly, like how to conclude how everything is, like how this follows. So just to recall the algorithm. The algorithm is recursive. So we have some parameter epsilon and L. L is like for the max level, and then there are this many parameters for the conductance. And what we do is that we just, given any graph, what we do is just we find a balanced sparse cut, right? And if we cannot find one, if this procedure say that H is already an expander, then we return it. And we said before that like this L is actually gonna be at most capital L, because we will never increment it more than, like we have this thing, yeah, and this is proof, like this is an invariant, and this basically is proof here that actually so actually there can be like L-1 down edges, because if there are L-1 down edges, then you are at level L, and when L, small l is capital L, then this constraint is trivial, so you would never go down again, right? Which means what? Which means that when you say that, okay, this part of a graph is already an expander, so it means that this part of a graph is is at least phi, because we set phi to be, this is how we set phi, right? Phi is like this thing, and L here is at most L. So like the parameter really match, like we really get a phi expander whenever we stop. Okay. So first thing first, like the first thing to note is that, okay, each of the part is really a phi expander or better. Okay. And the next thing is about how many edges are crossing the partition. Well, we know that whenever we cut through anything, like when we fire a sparse cut, this is like the sparsity of the cut is at most phi 1 times this thing times the complex like the approximation ratio. Like, and it can be phi 1, and phi 1 is the biggest, right? But even for phi 1, it's still at most phi times polylog, like log to the L, something like that. So it means that basically every cut that we found is phi times log to the O of 1 over epsilon in sparse. And then we use the same argument as we did in class. Like once we know that we always cut sparse cut, the total number of edges that we ever cut is gonna be like the total number of edges that we ever cut is gonna be this thing times m times log m, right? Is this okay? Yeah. So basically the fraction of edges that we ever cut is something like this. So this is why we can conclude that the first thing is correct. Every part is a phi expander, and the total fraction of edges that we cut is something like phi times this polylog. Okay. And then so this is what we get, and to analyze the running time, we just compute like bounded number of the depth of the recursion. And just to recall, we have seen that if you look at any path, like any root to leaf path in the recursion, then like in this path, we said that there are 3 types of edges. There are just log n left edges, and between this log n interval, there can be at most L down edges. And now inside between this left and down, between any 2 consecutive left and down, there can be at most R right edges, and we bound R to be something like, we have bound R to be something like this. Like this time, something like log. And once we have that, then it means that the total length of the path is going to be like, this is for left, and between any left, you have this many down, and between any left or down, you have this many R. So that's why the total length is this much, okay. which is something like m to the epsilon. Which is why we can just say that the algorithm basically calls a bound cut in graph of total size like m per level, and there are something like m to the epsilon number of level. So the total size of the graph that we call this thing is this much, this many edges. And because we know that the bound cut also can be solved in nonlinear time, that's why the total time is m to the 1 plus epsilon. Yeah. So if you set epsilon to be a constant, then this is going to be polylog, and this is like almost linear, but it's slower than linear by a polynomial factor. But you can always like trade this off. Let's say we set epsilon to be actually smaller than a constant. Then the running time here is going to be m times this thing. And this is like a subpolynomial factor now. And also this thing, when you plug epsilon in, you get this much. And this is also like 5 times subpolynomial. So just to conclude, what we get is that we basically, like in the best, like if you just want existential result, you can make this log m, but there is a fast algorithm to do almost the same, but you replace log m by subpolynomial factor m to the little one, and the running time is almost linear too. Okay, so that's what we have. Question about this result? Okay.
The algorithm calls balance cut in graphs of M, right?
What do you mean? Like there are, each graph have size maybe less than m or
Is it about at level I, sum of all the graphs is what is that size? In the recursion tree.
So the total size, like here I really bound the total size of the graph over all things.
Okay. So over all the levels. Okay.
Yeah. Okay. So actually this is like what you see here is the fastest known algorithm already. But actually there is another algorithm which is also fast and but it has incomparable running time and quality. There is another fast algorithm that, this is now polylog, right? Everything is the same, but this is now polylog. And, but the running time is this thing. So if, it's not always, it still depends on phi. Yeah. But this is faster actually when phi is big, and this is usually what we care anyway. Like we want to find expander decomposition when each expander is a good expander. Yeah. So, but I don't think I will have time to talk about this thing. Yeah. This is my This is my work with Huang, and this is also my work with Danupon and Wolff-Nielsen. Okay. All right. So I just would like to stress the flexibility of what you have seen of how to compute expander decomposition that you have, like this algorithm in class that I mentioned. So basically, first of all, once you have defined a notion of sparse cut, then it just follows what should be an expanded decomposition corresponding to that sparsity, right? What expanded decomposition is really what you get after you keep finding sparse cut and recurse, keep finding sparse cut and recurse. You've defined the notion of sparse cut, you get a corresponding definition of the expanded decomposition. And so let's try to define this. I will give you like maybe 3-5 minutes to think about. If we can, if now what we are given is a graph G and this demand vector and then also a parameter phi, then and just to recall that this the expansion of any set is defined to be the weight of a cut over mean. Then now we have defined a notion of sparsity. What should be the corresponding expanded decomposition for this notion? Yeah. So yeah, I'll let you try.
So we will get log of d on v also in our because every time we cut and recurse, so the small thing can, if it's not, assuming it is balanced, now we will get. But getting balance cut in d is also done similarly.
So yeah, something like that, but yeah, I will just wait a bit more and then okay, so yeah, so what we should get is that first of all, for each of the part that we get, like if we keep finding sparse cut until we cannot find, and what the algorithm return is this part, then for each of the part, well, it will be the D expansion of each part is big, is phi. Now we just need to ask what is this, right? And we would have that the total weight of everything in between each part. This should be something like 5 fraction times the total demand here times log of dV. Okay. So for example, if say that, like just to be more concrete, if suppose that you have some terminal set, call this T, this set T, and then if you just say that, okay, you set the demand to be just 1 if V is in T, and 0 if V is not in T, like, then what you would get is that this is gonna be 5 times T times log T, right? And so you will get that, like, okay, maybe this is T. So the total number of edges crossing each part here really is proportion to T. It's not like, it doesn't depend on the whole graph. And, but what you also get is that on each part, okay, on each part, that this part might not be an expander, but the terminal inside each part are well connected, right? To have D expansion large, when D is defined this way, it means that the terminal inside each part are well connected. Or another way to think about this is that you can embed a clique between expander. Like you can embed the one product graph between the terminal in the part into this part. Make sense? Yeah. This is just what it means to have this thing large. Yeah. You can embed the one product graph, or you can embed an expander into, like, you can embed an expander where the node is the terminal in this, into this part. Say it again.
What is the congestion?
The congestion would be 1/5. Yeah. Right. Just like in normal graph, if the graph is a phi expander, it means if the conductance of any graph is phi, it means that you can embed an expander in any expander into this graph, like any one expander into this graph with congestion like 1/5 times log n. There is some loss of log n because of flow cut gap. Yeah. Okay. So you can try to define, okay, hypergraph, you can do it too, but let's do this, vertex expansion. What should we get? Well, what we get is that, let's try to do it now actually. So what we will get is that, okay, if we keep finding sparse cut, now it's a vertex sparse cut. So you need, like, if I say that I find this vertex sparse cut, now this is not edges, right? It's like, it's a vertex sparse cut. So there are really some vertex here. Then maybe I say that, okay, once I find this vertex sparse cut, I remove all these vertices from the graph. And let's say this is L side the separator and R side, then I recurse on GL and GR. Yeah. Like there is some choice to be made here. Actually, like do we want to actually recurse on G of L union S and G of R union S or not? But so there are some choice to be made. But let's say for simplicity that we really just recurse on the two side where we destroy S. Really, just when we find sparse cut, we just remove the separator. Okay. Well, if we keep doing this, then you can, I guess, you can see that and repeat until we cannot do it. Then what we will get is like, what we will get is a set of node. Again, but there will be another set of node, which is a set of node that we removed so far. So maybe call it V0. And then we would have that for all I that is more than 1, then the vertex expansion of this part is now big, and we would have that the total size of V0, how big should it be?
Phi n log.
Yep. Phi n log n. Right. And now this is now n because, yeah, like you just really say that. I guess it makes sense, right? Like you find sparse cut, and you say that the sparse cut here is charged to the smaller side. And now each node is charged just like a phi factor. So each node is charged by phi, and it can be charged log n times. So you get phi n log n. Okay?
So this log n times only comes by assuming that we are getting a balanced cut everything.
No, we don't need to assume that, because even if you just like the first argument when I talk about just the existential of expanded decomposition, even if you get unbalanced cut, well, you charge this thing to the smaller side. So the vertex is charged whenever it is on the smaller side. It doesn't matter if this cut is balanced or not, right? But when you get charged, your graph is reduced by at least half. So the bigger one is not charged. The guys on the bigger side is not charged anything. Yeah. Okay.
Because the definition of expander actually always takes the smallest one in the denominator.
Yeah, exactly. Exactly. Okay. Now what about directed graph? This is now quite interesting. So let's define the notion of sparsity in directed graph to be this. Like I would say that the graph is like the cut here is sparse if either there are small number of out edges or small number of in edges. So this is like so I take the mean of both directions of the cut edges over the volume as before. Okay.
New definition?
Well, it's not new. But we didn't see it in class before. Yeah. Yeah.
Because now there is asymmetry coming in, right? Because we can take the bigger side and then define the cut towards that and or away from that as well.
No, this is symmetric. This function, this thing is symmetric, right? Like if you replace it by this thing, it's the same. Right, because I take mean on the guy in the numerator and I take mean on the denominator too.
Because it is minimum in the numerator as well. Then.
Yeah. Yes. Okay. So why do we define the expansion in directed graph, right, like this? Because I mean, there are like several reasons, but one reason is that if you say that the graph has high expansion with this notion, have high conductance or expansion with this notion, then like the nice theory that we have developed from the first half of class, like you're gonna get that like you can, if this is true, then you can embed directed the product graph into this too, and the random walk, you will get that, like the random walk will mix well, that will be true as well, and so on. Yeah, so it seems to be the right notion. Yeah.
So because there are, if whatever we are taking in the numerator, if there are x edges going in one direction, then there should be at least x edges which should be going in the other direction as well. That is why mixing happens.
Yeah.
Whatever x ratio we are getting.
Yeah, that's an intuition. Yeah. Like making sure that everything really transfer, like needs some real work. Like, but yeah.
But at every cut we are actually having x and x, right? So it's as good as 2x directed edges versus x undirected edges. So the mixing and everything basically, the flow embedding, everything happens exactly right. At every cut.
I mean, yeah, I agree with this intuition, but like for example, like we have, when we talk about flow cut gap, okay, we talk about like metric embedding, and that is like, it's not clear how to talk about metric embedding for a directed graph at all now, or yeah, but that's the correct intuition here. Yeah. Anyway, given that we define the notion of expansion in this way, so let's try to derive expanded decomposition for directed graph, right? So first thing is that there are like, what if the graph is something like a DAG, or let's say the graph is a path, a directed path. What would you get from expanded decomposition? Like if you say that you keep finding sparse cut with this notion.
Zero, right?
Yeah, exactly. So like you could find a cut such that the conductance is just zero because there is no edges coming in the different direction. So For example, here you will find, let's say this is a sparse cut, you will recurse on both sides here. You will find a sparse cut again, and here you find a sparse cut. Everything you really get like a trivial partition. That is, everything is just, like each expander is just a node. So it seems to be like the case that, and see, what will happen if the graph is a DAG? The same thing happen, right? You will find there is a cut where there's not, like the expansion is 0. And you can keep doing this again and again. So when the graph is a DAG, it seems that like nothing is really going on. Like it returns something useless. Okay. But let's see. I mean, we see that, okay, it seems to be not useful for a DAG, but let's just try to see what will happen in general.
Connected, right? Then only the graph should be strongly connected, then only anything non-trivial will get.
Yeah, right. That is, if it is not a DAG, then there is something. Like strongly connected means that the graph is not a DAG, right? Oh, no. Like there should exist some strongly connected component in it. Yeah. So
every graph should be strong, the whole graph should be strongly connected, right? If not,
no.
you find the sparse cut of 0, right?
Yeah, but let me go on. Well, because the whole graph need not to be strongly connected. Like if you have something which is strongly connected and this is a path, well, you can still define something useful in this part. Yeah. Okay, so let's see. Let's see what we will get. My claim is this. Let me just state what we will get. What we will get is that if you return the decomposition of this, you will get a collection of nodes again, such that for each part, it has, maybe I put directed here, and directed here. The directed expansion of each part is at least 5. And then, and this should be the case anyway. But note that some of Vi may be just one node, right? And then I will say that there is maybe I said that there is a subset of edges and subset of edges E prime in A. Think of A prime as the thing that we cut. Like when we find a sparse cut, like if we say that this is sparse cut and there are like if it is sparse because of this direction, then this thing will be included into E prime. Put it into E prime. Like we keep finding sparse cut and okay. So if we do it this way, then well, the size of E prime is going to be at most 5 times m log m, right? But okay. And my claim is that, so yeah, let's see. That now comes the thing that makes it, so let me define G to be minus E prime and contract like is obtained from G by removing E prime and contract each VI. Then the claim is that this is a DAG. So why is that? Like, let's consider the process, right? Well, you have any directed graph. You find some sparse cut. A and B here. It must be sparse in some direction. It may be like sparse, like it may be the case that there are many edges here, but few edges here. Then you just say that you remove this thing. But if it's other way around, I assume that A is on the smaller side, okay? If it's another way around, let's say there are few edges here and a lot of edges here, then we remove this thing. But while after I remove, then I can just redraw it in this way, right? Now this is A, this is B. So now, if you look between A and B, there are just one direction from left to right. Yeah. Okay. And now we recurse on inside B and inside A. Yeah. And what you will get inside A, B, and A is that you will keep finding some more cut, and like there are, and you make it such that there are just one direction, and you might remove some few edges here. And you keep doing this and again and again. Well, the total number of edges that you will remove is gonna be this much, just by the same charging argument. And then like when you stop, let's say you cannot find any sparse cut here, then it means that inside this part, there is no sparse cut in any direction. So if you stop here, then you get an expander. And so if you stop, it means that it is super strongly connected. Like for every cut you get like strongly connected means just that if you look at any cut, there are some edges on both sides. Here it says that it's an expander, so there are like a lot of edges on both sides. So this is what it means by expander in the directed graph. It's super well strongly connected. Yeah. But anyway, if this is, let's say this is what I end up with, like at the end, everything here inside is very strongly connected. But if you contract them, then you get a DAG. If we remove the E prime from the graph. Yeah. So Yeah. So in the directed graph, you can say that, okay, every graph is a disjoint expander with few crossing edges. In the directed graph, it's not as simple, but it's still kind of nice to know that every directed graph, if you remove few number of edges from the graph, is a DAG of expander. Directed graph is small fraction of edges plus DAG of expander. This is the case for every directed graph. Yeah. So this notion can be useful actually. I sometimes use it for some dynamic algorithm, but yeah, that's for later. Okay, anyway, so we have seen that this notion of decomposition is just very flexible, just adjust for all notion of expansion. But the algorithm that we have seen is also flexible in the sense that, okay, once you have defined a notion of sparsity or expansion, you just try to define a balance cut a subroutine for that kind of expansion. And but balance cut subroutine is solved using cut matching game. And cut matching game actually is very flexible to all kind of expansion, all notion of expansion too. So the upshot is that for almost basically all kind of expander decomposition that you want, you just need to call a bunch of balance cut subroutine. What we've seen is really a reduction from decomposition to balance cut subroutine. And balance cut subroutine is reduced to polylog of approximate max flow because it can be solved using cut matching game. Yeah. So whenever you want expanded decomposition, usually you can do it fast. Okay. Okay. Yeah, I will try to guide you through the homework how come cut matching game is also very flexible. Okay. Is there some exercise? Okay. There is this exercise. Sorry, let me look through it. Okay, there's this and this. Okay. So about how to use cut matching game to find a balanced sparse cut. So I mentioned that what we need to do is really like look at the graph where like given two side A and B, you solve max flow and you just need to check if the value of max flow is more than A plus minus beta. I don't know, like this thing can be done just by writing some equation, and so should we? Yeah, you can verify this yourself, I think. Yeah, why this is okay. And let me actually then like just quickly. Okay. Okay, I let you do this. Like once we can either find balanced sparse cut or embed a matching, but with few fake edges, then you would be able to either find a balanced sparse cut or embed an expander with few fake edges. And we have seen that if you can embed an expander with few fake edges, then it means that there cannot be any balanced cut in the graph that is sparse. So this is this claim, right? If you can embed almost expander with few fake edges, then all the balance cut must be expanding. So if you can really like prove that you can you can solve this thing using one max flow, you just combine them together and get what we want at the end. So I guess this is fine. Okay. Yeah, let me just put this as a homework, as an easy homework. So okay, so maybe last thing, I would like to kind of philosophize thing a bit. So like try to look back at the cut matching game. We see from the first half of the course that when you have a graph with degree profile D, then the graph is an expander, is a phi expander if and only if you can embed a D product graph into your graph, maybe after scaling by phi, right? That is, the congestion is, or in other words, the congestion is like 1/phi. So there are some log factor lossing here, but yeah, essentially this is what we have. And but to solve this, to check if this is true, this is multi-commodity flow where